Okay, so today we're going to finish up the proof of the Fast Fourier Transform. And then after that, we're going to sort of head in the direction of how do you do Fourier analysis on general finite abelian groups. So some of that, I'm afraid, will be maybe just like endless definitions. It's it's the pattern of starting to like give all this sort of basic information and then show you the interesting part. But not everybody has had grouping, and so I think we should give that. Okay. So the Fast Fourier Transform, right? Is a theorem, right? Somebody gives you gives you the first non-trivial nth root of unity, right? And we're in the case and some power of 2, right? Then if you're given this guy, it takes at most 4 times 2 to the n times n steps operations. That is to say, something on the order of n log n operations to calculate all the Fourier coefficients of a function on Zn. And then, as we saw, there was this lemma, right? The key lemma. What was the point of the key lemma? Can somebody tell me?
You divide to the even powers.
Right. So you take your function and you divide it into the even guy or the odd guys. Okay. If you don't know what to call something, you can call it a guy. That's the rule of mathematics. Although when I took my qualifying exam at the University of Chicago, and I said, "So you have this guy," blah, blah, blah. The professor said, "What is a guy?" Okay. So you take your function and you divide it into these two guys, the odd guys and the even guys, right? And you say, okay, well, look, then basically what that tells you is that the Fourier coefficients of the initial guy, right, can be computed in terms, which is on z2m, right, is controlled by a computation of the Fourier coefficients on zm twice, right? You need to do the odd guy and the even guy, right? So the point is that the number of steps it takes to calculate something on z mod 2m is controlled by twice the number that it takes you to calculate the Fourier coefficients on z mod m plus some small factor. Right? So that actually turned out to be almost a tautology. Okay. So that's where we were, and and so the proof. So we finished that, right? And so the proof of the theorem is then by induction. Right? And it's pretty straightforward. I don't even know if I want to do it, but I'll do it. So we induct on n where n, capital N is 2 to the n, as we said before, right? In the case n equals 1, and capital N is 2, of course, right? Then by definition, A naught and F is 1/2 F1 plus F minus 1, right? A1 by definition, right? This is that, and A1, so the 0th Fourier coefficient is this, the first Fourier coefficient. is this, f1 minus f minus 1. Right? And so you just count up how many operations you have. Right? You've got 1, 2, 3, 4, 5. So you count 5 operations. So case 1 is done. So
Can you just briefly go over the counting the operations again?
yeah. So there's an addition.
Yeah.
That's 1. There's a multiplication. That's 2.
Okay.
Right? Here's a multiplication. You've got minus sign. Right? So there's a multiplication first. Right? So multiplication, and then there's an addition too. Right? The subtraction is an addition and a multiplication. Right? And then the multiplication here. Right? So you've got 2 operations and 3 operations. So 5. Okay. So 5 is less than 8. 5 is less than 8, and so this is okay. Okay, and then so then you assume, simply given by induction, assume the theorem for the case n equals 2 to the n minus 1, right? In other words, that the number of steps to calculate n is controlled by 4 times 2 to the n minus 1, n minus 1. So this is what we can assume by inductive hypothesis. Right? And you want to show that we want the case for 2n, right, to get the next step. Right? So right, we want this thing to be controlled by 4 times 2 to the n minus n. Right? And so obviously we use the lemma. Right? By the lemma, you know that this thing is controlled by twice this guy. 2 times 4 times 2 n minus 1, n minus 1, plus 8 times n, that's 2 to the n minus 1. Right? And if you work that out, that ends up being 4 times 2 to the n minus n. And so that's what you want to do. So once you have the lemma, as you see, the fast Fourier transform, is basically all in this lemma, and the lemma basically gives you the algorithm, right? You see what you need to do. If you have something, you just break into the odd and even parts, break those odd and even parts into their odd and even parts, break those odd and even parts into their odd and even parts, go all the way down to the bottom, right, and go back up again. So the algorithm is built into the proof, and that's a really cool thing about like if you look at the different, for example, in the case of the Radon transform, if you look at the different proofs of how to reconstruct the Radon transform, each leads to a different technology, right? So the different proofs each correspond to a different approach, right? And a different way of implementing the Radon transform. Same thing. The technology is in the proof. So Fast Fourier transform, known to Gauss, 1805. I think that happens more often. That's like a usual ending to a story. Right? This was discovered by so and so, but in fact, it was many years later. It was found that was known to Gauss. It was like in Gauss's office drawer or something like that.
It's like you name everything after the first person actually know what you discovered.
hard to tell what things are. Yeah, somebody was just saying, I explained, e to the I theta equals cosine theta plus I sin theta, Euler's formula, and people are like, why do they call this thing Euler's formula? It's so trivial, right? Euler there must be hundreds of things that could, of greater value that could be called Euler's formula.
You know Stigler's law?
What's Stigler's law?
It says that every theorem in mathematics is not named after the person that discovered it.
That's right.
So, Stephen Stigler, the corollary is that Stephen Stigler did not invent Stigler's law.
Yeah, I think I mentioned that the Radon transform actually, some people would insist that it should be called the Fourier transform. So the next thing we're going to do, so this was an application of Fourier analysis on a particular abelian group, right? A very simple abelian group, Z mod n, right? Z mod n, right? And so you might wonder, is it possible to do Fourier analysis on other groups? And if you do, what do you need to set up, right? What do you need to set up? What do you need to have in order to create a theorem on that group, right? So we will talk about Fourier analysis on finite. It turns out that it's possible to create a working theory of Fourier analysis on finite abelian groups. In fact, as I said before, in fact, it's possible to get rid of this term finite and instead talk about so-called locally compact abelian groups. Okay, those of you who have had some topology before, locally compact means that every point is contained in a neighborhood, which is in turn contained in a compact set. Okay, so every point that you've got, you can find a neighborhood around it that's contained in some compact set. That means you're locally compact. Okay. Of course, if you're finite, you're certainly locally compact, right? Right? Because you're just a bunch of discrete points, right? Here it is, the neighborhood that is locally compact. Right? It's finite. I'm laughing. So you might wonder, just in case you're curious, and are wondering, what does locally compact do for you? Locally compact, I think I'm not lying to you. Am I lying to you? Okay, I think I'm not lying to you. So locally compact, basically, so you think about what's going to happen. You're not going to be on a finite group anymore, right? It's not finite anymore, and so you're not dealing with sums. Right? You'll be dealing with rather infinite sums, or actually not infinite sums, because it could be continuous. It could be a continuous group, right? So then the question. So then what's the problem? The problem is that you need an integral, right? Well, how are you going to get an integral? You need to have a measure to integrate over your group. Okay, and so this condition. Basically guarantees the existence of a particular kind of invariant measure, a measure that doesn't change when you multiply it by the group operation. Okay, so a so-called Haar measure. Haar measure. And once you have that, then you've got your integration, and then you can basically do as you've done before. Okay. Yeah.
What do we need to talk about neighborhoods and such on a group? We don't have a notion of open sets.
That's right. So the group has to be given a topology. Okay. So yeah, so when we talk about a group, we really mean a group, a so-called topological group. Okay. So locally, people just assume this. So yeah, it's cool, right? You don't think about topology in groups when you take your algebra course, but in fact, you can put a topology. You can put a topology on a group. And you want to do it in such a way that it's compatible with the group law. Okay, if you do it in a way that the group law is continuous with respect to the topology, then you have a so-called topological group. Okay. And then it makes sense to talk about local compactness. So maybe things that you didn't think would intersect actually do intersect very strongly. Okay, so really all of this can be done in a much wider context. Okay, but we're not going to do it. We're going to stick with finite abelian groups. Okay. So let's give the general definition again. I think many of you have seen this already, but there's no reason for me not to do it properly. So the abelian group is just a set. It's a set G with a binary operation. Binary operation, a so-called group law. You think of this as a multiplication, on pairs of elements. So you have a map taking pairs of elements, and then you map to something called A dot B. Okay, so it's just a way, you have a set, and you have a way of multiplying things in the set. Okay. With an operation that satisfies one, that A dot B equals B dot A, two, A dot B dot C equals A dot B dot C. Three, there exists some element U such that A dot U is A for all groups, for all elements. And four, for all elements in the group, there exists something called A inverse in G, such that A times A inverse is the unit element, the identity. So, all this is saying is that you have a set and it has a multiplication on it, and this multiplication behaves pretty much like our what we think multiplication how it ought to behave, right? That it's commutative, associative. There's an identity element. There's a 1, right? This is usually denoted by E, or 1. And there are inverse elements. Okay, for everybody in the group, there's an inverse element. Okay, somebody you can multiply by and get back to U. Okay, so for example, if I look at the real numbers and with the standard multiplication, right? Say I look at this pan, here's my set of elements, and here's my group law. Standard multiplication. Is that a group? Well, this is true, this is true, this is true, this is false, right? It's not true that everybody has an inverse. 0 doesn't have an inverse. Okay, so it's not a group. Okay, but if I look at R and I draw the 0, okay, and use the standard multiplication, is that a group? Is that an abelian group? Yeah, sure it is. Okay. If I look at Z, and if I look at R again, and use plus as the group law, is that an abelian group? Well, it's true that A plus B is B plus A plus B plus C is the same as A plus B plus C. There is a unit element, namely 0. When you add 0 to anything, it doesn't change. Right? A plus 0 is always A. Are there ways to get to 0? Is there going to have a way to get to 0? Sure, you just add a negative. Right? So everybody has an inverse under the group law. Right? So this guy's right? So this is an empty group. Right? Right. Earlier we mentioned that if we look at the matrices, let's say the 2 by 2 matrices with determinant equal to 1. Right? If we look at those guys with matrix multiplication, right? Well, is that an abelian group? No. Because it fails the abelian. It's not abelian. It's a group, it's not abelian. So it does satisfy, a group, this is a group, but not abelian. Because the commutative, matrix multiplication doesn't commute. Okay. However, it does have associativity. There is a unit, right? There's a unit in there, the identity matrix. And if you have a 2 by 2 matrix with determinant 1, there's an inverse matrix that also is in that set, determinant 1, that you can get to the identity. That multiplying gives you the identity. So just some examples. Another example, let's just look at the rotations, say, on R2. The set of rotations on R2. Is that it? You take your thing and just rotate it, no flipping the rotation. That's also a group. Right? That's a group. Right? Because if you sum 2 rotations, well then you get the same rotation if you sum them in different orders, blah, blah, blah. Is there a unit element? Yeah, a rotation that doesn't rotate, right? Is there a backwards rotation? Is there an inverse rotation? Yeah, a rotation that rotates in the opposite direction. So this is also a group. And as you see, it's as you might guess, it's isomorphic to S1. Right? Isomorphic to the circle. The group of things of modulus 1. Okay. Definitions that we're going to need. Let's consider Z mod Q. So Q is some natural number, and consider Z mod Q, and let N be some number in Z mod Q. And the book and I will sort of not distinguish between the number and its equivalence class. So we're going to conflate them. It'll be sort of clear what it means. Okay, so suppose you have some N in Z mod Q. We say if there exists an M in Z mod Q such that N times M is 1 mod Q, then we call N a unit, and write N is in Z mod Q star. So you put the star on to indicate that's the units. Okay. So like if you're in Z mod 4, well then 2 is not a unit, right? Because 2 times 2 is 0. And you can't multiply by anything to get to 1. Right? But right, so this is an order of G. It's just saying how many guys are in the group. So this is just a notation. And what you do in group theory is, of course, prove all sorts of results dealing, relating the order of the group to the structure of the group. Theorems that are forgotten 20 years ago. Be cool to teach an algebra course, so I can remember it again. Okay, everyone all right? So groups, there are two important notions. There are a couple of important notions. So first is, so you've got two groups, G and H are groups. Okay, and each one has a group law, right? We write them both. We're going to write both the group laws as a dot, but depending on what will be the group, one dot will, depending on the context, it'll be the group law for G and the group law for H. Okay, so you have a map. Suppose you have a map going from G to H. If f of A dot B equals f of A dot of B, we call f a homomorphism. Same form. So basically, if you have a map that preserves the group law, right? The map, in some sense, preserves the group law. Right? Multiplication, when you have two objects that are multiplied in G, you pump them through the map, it turns out that you get the same thing as the product in H of the images of F, of A and B through the map. So that is, it commutes with the, it's more accurate to say it commutes with the group laws. So for example, an example of this, if we look at R with addition, that's a group, right? And we look at R plus with positive reals with multiplication, that's a group. Okay. Each of these is a group, right? So positive reals with multiplication, that's a group. R with addition, that's a group. And we look at the exponential function, right? That's a map that goes from the reals to the positive reals, right? And we see that the exponential function of e of a plus b is e of a times e of b. Right? That the exponential function of a group law b is exponential function of a group law exponential function of b. Right? Where this group law, the group law here is plus. Right? X of a plus b is x of a times x of b. Right? So this is an example of a homomorphism. Is that idea okay for those of you who haven't seen it before? Okay. So you have a map, you have these things called groups, they've got this multiplication on it, right? And you define, you say, you've got a map from one group to the other that basically preserves the group structure, preserves the group structure in the sense they call it homomorphism. Another definition, if a homomorphism is also one-to-one and onto, right? So injective and surjective. Right? That is to say, it's invertible, right? An invertible map. Then we say it is an isomorphism. A group like isomorphism, and we write that G is isomorphic to H. This is basically the same thing as saying that there is an inverse map that's also a homomorphism. It's equivalent to there exists an inverse homomorphism. From H back to G. Amy, have you taken abstract algebra? Yes. Good. Okay. Sorry to keep on going like this, but there's another definition. So given two groups, G1 and G2, two groups, we define G1 cos G2. So this will also be a group. And basically, it's the set, it's just going to be a set of pairs of elements. G1 is in G, G2 is in G2, so G1 is in G1, G2 is in G2, of course. Why would I do the opposite? Right, so this is the set, it's just a Cartesian product, right? And you define the group law, so you define this thing by blah with the obvious group law. Right? The obvious group law being G1, G2, group law, G1 prime, G2 group prime, G2 prime. Well, that's just going to be G1, G1 prime, G1, G1 prime, G2, G2 prime. Where this is the law that we're defining, and this group law is for G, like multiplication in G1, and this one is multiplication in G2. So you're given these two groups, they have their own multiplications. You define the multiplication on the product by using the multiplication on the individual costs. Is that obvious? If these guys are abelian, then this guy is also going to be abelian. Okay, and the authors, just for your edification, mentioned something called the structure theorem for finite abelian groups, which is this, that if G is a finite abelian group, then G is isomorphic to some direct product of things with the form Zn, so Zn1 cross Zn2 cross Zn. So any finite abelian group can expressed as a direct product of these things that we're familiar with. Okay. These simple guys that for whom we already have done Fourier analysis.
So it just means that the Fourier analysis we've covered will always hold on any.
Sort of. It sort of means that you could build up for any finite abelian group the Fourier analysis on it by doing it on the pieces. Okay. But we're actually not going to do this. We're not going to use that. We're going to pretend it doesn't exist. Okay. So this is just in parentheses. And the authors are right, you know, because we don't need. We're going to create the Fourier analysis on the general finite abelian group without. We don't need. We'll go around it. Maybe the authors are showing off. We couldn't do this easy way, like pulling out the big machinery, pulling out the machinery from the abstract algebra. But we're not going to. Why should we? We're analysts. Okay, so now, great. I think that's it for the algebra background. Well, later on we'll sort of go back into it. Or that will actually go backwards into the linear. Okay, so let me just erase the whole board. Cleanse it of any algebra. So I'm going to put algebra back on it. So okay, so now we're going to talk about something called characters, and we mentioned this term before. It's the analog of the functions that you use to reconstruct your functions. Okay. So let S1 denote the unit circle. And C, right, with complex multiplication. That's the group one. Right? It's of course everything with the form of e to the theta. Right? Theta. So here's the definition that we want. Here's how we generalize. Given G a finite abelian group, and you have some function E going from G into S1. If E of A times B in the group always is E of A, E of B, this is complex multiplication, in other words, the group law of S1. In other words, if E is a homomorphism, if E is a homomorphism, we call E a character of G. Okay, and we let G hat be the collection of all characters. So you can sort of predict what's going to happen. Right? We're going to look at the functions on finite abelian groups, and it'll turn out that we'll have some sort of inversion formula, right? Allowing us to get Fourier coefficients and use those things to reconstruct functions as combinations of characters. Okay. At this point, you might ask, what's so special about S1? Right? You might ask, can we think about mapping G into some other space? For example, spaces of matrices. If you take in representation theory, you know that that's exactly what you do in representation theory. That you map your G into spaces of matrices, and then you figure out information about G from the maps, from the representations. Right? So harmonic analysis on Lie groups, that is, groups that have both a manifold, groups that have a so-called manifold structure, is basically representation theory. So that's, if you want to do harmonic analysis on groups in general, it intersects with, it basically is representation theory. So it's all tied together. Sometimes I wish that I had gone that route. It's sort of cool to have, you've got, you're doing your analysis, but also a big factor is the structure, the algebraic structure of the group that you're working on. So it actually makes it a bit richer than just doing harmonic analysis on Euclidean space, although close to Euclidean space has some of those properties as well. Okay, so going back, right, so we have these guys, we have a group, we have these maps, the maps are homomorphisms, and they are, we call these guys characters. It is an easy exercise to say that if we define for E1 and E2 in G hat, a product, a way of multiplying these guys, E1, E2, by saying that E1, E2 at some point, for all n G, we say that E1 and E2 of A is just E1 A times E2 A. If we do this, then we define the multiplication on the collection of characters, right? So we have all these characters, and we define a group law for them, and this this multiplication makes G hat an abelian group. Okay, and so this thing is called the dual group. Okay. And at this point, we don't know too much about this group. Like, how big is it? How many elements does it have? Is it a finite group? We'll see soon that, in fact, it is a finite group, and it has the same order as G. It's the same size as G. Okay. So far, we've got this thing, the dual group, right? We've got a group, we've got characters, they themselves create another group. You might ask, what is the dual group? The dual group is the dual group of the original group. It is. It is something called Pontryagin duality. Anyway, go read Rudin's group on local combat, the local groups. Okay, let's finish with one lemma that will be useful. That basically allows us to get characters. G again, a finite abelian group. Group, and E, let's suppose that E is just a map from G into complex numbers. Okay. If E is multiplicative, In other words, E of A times B equals E of A times E of B for all A, B, and C, and G. Then E is a character. So this is saying that if you have any map into C, right? If you have any map into C, right, you don't know that it's mapping into a unit circle. Okay. But if you have any map into C that's multiplicative, then it has to map into the unit circle. Okay. And the proof is sort of cute. Okay, so here's the proof. We say, well, look, E is bounded above and below. Right. E is bounded above and below. Right. Right. Because this is a finite group. Right. So it's clearly bounded. And
couldn't we just get this condition by saying E takes everything to 0?
E takes everything to 0. Yeah. What's that?
C is
And C minus 0. Okay, yeah, okay, thank you. Okay, so let's consider function, it's bounded above and below. Okay. And then you say, well, look, if for some, you choose any G, if E of G is greater than 1, well, then E of G, then E of G to the n, right, to the nth power, will go to infinity, right, as n becomes, as n goes to infinity, right? But by multiplicativity, you know that this is the same thing as E of G to the n, right? But that would mean that there are elements for whom the function becomes arbitrarily large. The function has to become arbitrarily large, and we know it doesn't, right? So this is impossible. And similarly, we know that this thing is bounded away from 0, right? Because this thing is bounded away from 0, and if we had that E of G in absolute value was less than 1, we play the same game. We say, oh look, that the limit of these guys gets arbitrarily close to 0, right? And that's impossible too, because it's a finite group. And so there must be some point, there must be some point lower than which we cannot reach. And so that's the end of that. So this will be useful in the next lecture. And so next time we'll see that the characters are actually the things that we want, right? That these are the guys that will allow us to get a Fourier inversion much well, etc. Have a nice break.